Alright, here's we did some video solutions of a couple of these problems. Let's talk about the first one. There's actually enough room here to work the problem, but I'm going to go to a blank piece of paper. So the idea is we're given this differential equation. And these are still new to you, so there's lots of possible misconceptions. Remember that this is x of t, and this is being differentiated with respect to time. So this is x of t. X of t is unknown. That's the problem, is to find it. Also, consider this differential equation versus, say, x prime equals sine of t. This one is literally simple in the sense that it's called the simple differential equation, and it's solved directly by integration. X of t would be equal to minus cosine of t plus some constant of integration. But you can tell that this can't be the solution of this. Right? If you were to plug this into that, just to check it, right, the derivative of this is sine of t. Does that equal sine of x? No. Nope. Not even remotely. So this can't be the solution of this. Anyway, that's an aside. Now what we're going to do instead is to figure out some stuff about it graphically. And we do that by sketching a graph. We do x prime versus x, and this is easy to graph because we know how to graph sine. We know lots of stuff about sine. And everywhere that it crosses the x-axis is an equilibrium. At each one of these points, nothing is happening. X prime is 0. So it's 0 at pi, at 2 pi, at 3 pi. Now what's happening in between these? The derivative is positive. So we're moving to the right. What's happening between these 2 points? The derivative, the change in x, is negative. How about here? The change in x is positive. So if we have arrows pointing at pi, this is stable. And this one over here is going to be stable too. All right, because sine continues. So these two are stable. Well, if you have arrows that are pointing away, you'll have some unstable equilibria. All right. So what we can do from these is we can sketch a graph of possible solutions. This is an x versus t graph. And so let's plot, so here's pi, and say here's 2 pi. Now those are possible solutions. One solution to the differential equation is that the system is in equilibrium, and then it would just stay there. So if your value of x was pi, that'd be fine. If x has a value of pi, sine of pi is 0, x prime is 0. If x prime is 0, then x equals a constant is a solution. So these are all solutions. Now, most of the time the system is not already in equilibrium, so what happens then? Well, if we start, say, right, a little bigger than 0, say right here, the derivative is positive, and so the value of x increases. And then the derivative is positive and larger, so we increase, and then it's even larger, and so on and so forth. But then it gets smaller again, right? So we're increasing fast and then slower. And if you start halfway, which is pi over 2, you're increasing, but always less and less. And every other solution is just some version of that. But all these solutions will have an inflection point whoops, look right there, right through pi over 2. They're always going to change concavity, if they change concavity at all, right to that point. So when you're practicing these, I want you to be very, if you're not following along, then pick a point and really think about it. If x has this value, bigger than pi, right there, what is x prime? It's this value right here. What is it? It's negative. So we're decreasing. What happens next? Well, if x decreases, it's more to the left. Now it's decreasing, but less. What about now? Now it's less, but it's decreasing less. As we get closer and closer to the equilibrium, the magnitude of our derivative gets less and less and less. Our curve flattens out. It's more and more shallow. Right? You want to make these kinds of discussions. If you start here, what happens? I'm decreasing. Then I'm decreasing more. Then I'm decreasing more. Then I'm decreasing the most, but then I'm decreasing less. So it's those kinds of discussions. And thinking about how does the size and magnitude of this derivative affect the shape of this curve? Small, negative derivative, bigger negative derivative, biggest negative derivative, less negative derivative, less negative derivative. Also, concave down, concave up. Concave down is when the second derivative is negative, which is when the derivative, what do I want to say, is becoming more and more negative. It's decreasing. Okay, so it's bigger and bigger in magnitude, but it's more and more negative. And here's concave up. So concave up, the derivative is it's increasing, right? It's getting more and more towards 0. So connecting these different statements takes some practice at first, and we'll continue practicing. But you should be able to make these kinds of curves. And for the sine function there, it's pretty nice because it just repeats itself. So you'll have things like this, whatever, stuff like this. Here's minus 2 pi, same kind of thing. Halfway through, you'll get just concave down. A little further, you'll have stuff like this. So notice that these stable equilibria are attracting solutions. The unstable equilibria are repelling them. So this is stable, this is stable, this is unstable, this is unstable. Okay.